Greetings, I'm Steve Miller. Welcome to Lecture 3 of the Regression Unit for the LACOL Data Science class. And so what I want to talk about now is extensions of linear regression. So right now, all we've been able to do is find the best fit line y equals ax plus b. Unfortunately, most relations in the world are not linear. And if we could only use this to find linear relationships, it would be of limited use. So I want to show now how we can use this to solve a variety of other problems. So, as was remarked, we did y equals ax plus b. All that mattered in what we did is that it was linear in the unknown parameters. So by doing a little bit more bookkeeping, it turns out we could easily handle the case where y is a1 f1 of x plus a2 f2 of x plus yada 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 plus ak fk of x. We don't need the functions f to be linear. They could be anything we want. All that matters is that it has to be linear in the unknown parameters. We can't have an a1 squared or an e to the a, or a cosine of a. And that's because when we take the derivatives, it has to be very nice. This also gives us an opportunity to talk about notation. When we're doing y equals ax plus b, we could have also said y equals a1x plus a2. But we used a and b because since we only had two variables, it's nice to give them a different name. It's nice to avoid subscripts. When we start having an unknown number of variables, it's nice to just use the same letter for each one of them and then just have a different index for each one. So most relations, as I remarked earlier, are not linear. For example, we've talked a bit about gravity. So F equals g m1 m2 over r squared. So F is the force, g is Newton's gravitational constant, m are the two masses of the objects, and r is the distance between them. Imagine we guess that the force is proportional to a power of the distance between them. So we guess the force is some constant b times r to the a. Well, if we take logarithms of both sides, this gives you an example of why we care so much about logarithms. We would get the log of f, and then we get the log of b r to the a. The log of a product is the sum of the logs. So we get the log of r to the a plus the log of big B. And then the log of r to the a is a log r. And we're using the log of a power is the power times the log. And so I'm going to use little b to denote the log of big B. And now you might actually get some idea of why I chose to use a big letter for the constant and a lowercase a for the exponent, because I know when I finish the calculation, I will get something that's linear. And so now we get the log of f is a log of r plus b. So we have a linear relationship between the log of f and the log of r. So if you want to put this in the language we did before, the log of r, that would be our x. And the log of, that would be our input. And the log of f, that would be our y. That would be our output. And what we could do now is we could go to the lab and we could observe attractions between different, say, fixed masses at different distances and use this to sniff out what the relationship is. As another example of just the power of logarithms, there's a reason why we spend so much time on logarithms. Here are 25 of the most populous cities. Now, whenever you have lists like this, you really should state where they're from. I don't really care. I just really want a data set to talk about. One of the problems is your definition of what is a city. You're talking about the metropolitan area. You're talking about the city proper. So let's just take these as 25 values. So if I plot them, this is a nonlinear relationship. If I plot the rank of the city versus the log of the population, so the log of the population is down here, and the rank of the city, the large, second smallest, etc., the large, etc., still doesn't look so nice. But now if I plot the log of the rank versus the log of the population, I have a linear relationship again. And so just using Excel, very simple thing, you can do this in R, you can see quite easily that we are getting another linear relationship, and linear regression will be applicable. Another nice example is frequency of word counts in the English language. And so plotting the rank of the word versus its occurrences. And so the most populous word is occurring the most. When I take a log-log plot, you can see it looks pretty linear. Not perfectly, but there does seem to be a linear relationship. So I want to end with some other examples. So the first is a real-world challenge. So I serve as a member of the Mount Greylock Regional School Committee. Anything I say now is just my own personal opinion as a mathematician, and in no way should be taken to be any official statement from the school committee or the district. We originally had 3 school districts: Williamstown Elementary, Lanesboro Elementary, so one in each town, and then a shared regional middle high school. Amazingly, we actually had 4 school committees for 3 buildings. That's another story, though. We had a school budget of a little bit over $20 million for the 3 school buildings, and each one of them had their own budget. And when we were 3 different school districts, the state gave what was called Chapter 70 aid to each school. And we got about $3.5 million a year to the 3 schools. Unfortunately, once we regionalized and became 1 school district for the 2 towns, the state would no longer tell us how much money would go to each school. They would only tell us how much money went to the whole district. We wanted to allow each town to have local control over their elementary school. This was extremely important. And to do that, we needed to know how to assign the money in future years. The state has a formula, it has lots of variables, they keep it secret. But we can observe the values of the variables, and we can observe the amount of state aid that went to the 2 towns, that went to the 2 elementary schools and to the middle high school. And we can use this to sniff out an approximation to the formula. So this is a great example of the power of regression. So ideally, we would love a fair formula that does a great job predicting. It's transparent, it's easy to explain to the select boards, the finance committee, the voters, what's going on, that there's nothing that's hidden. It's clear how it works. And so I used the method of least squares or linear regression. And what was nice is I could get a really good fit without using too many variables. All I really needed to use was the populations of the 3 schools: Lanesboro Elementary, which is less pop, Williamstown Elementary School, which is West Pop, and the Mount Greylock, the middle high school population. And then the other input was the assessment of towns. This was basically like the net property value in the 2 towns. And so this is a little bit more involved than what we did before. Before we did y equals ax plus b, we had 2 parameters, a and b. Now I want a combination of less pop, West Pop, Mount Greylock pop, assessment in Lanesboro, assessment in Williamstown, and maybe also a constant term as well. So now we would be doing a linear regression, but with 5 or 6 parameters and not just 2. If you are comfortable with matrix notation, it's not that bad to do this and just do it in terms of some nice matrix X. If not, you can still write it out the long way. The point is a lot of programs like R can do all of this automatically. And you can just tell regress on these following. It turns out that there's a lot of desirable properties you want your solution to have. We are trying to come up with a formula for the 2 towns to use to assign money. We want the solution to exist. We need to figure out how much of the aid to give to each school. It should be between 0 and 1. We want something that would be stable under small changes. If 1 or 2 businesses close or a few kids move out of the town, we don't want that to massively change how much money the formula assigns. And not surprisingly, we want the sum of the 3 percentages to add up to 1. We can't distribute more money than we have, and we don't want to leave any money on the table. What's nice is the solution possesses all of these properties, and a lot of these you can prove theoretically. Here's a plot of the data that I used. And so this is the percentages of the money that went to the 3 different schools over the past couple of years. And so the dots is what we actually observe, and then the straight line is basically trying to do, the dots is what we observed. And so we can see terrific stability. Things are not changing by that much. And we have, the predicted and the actual lines. You can see that they're extremely close. So for instance, for the Williamstown Elementary, it's almost a perfect. For the Lanesboro Elementary down here, a little bit of fluctuations. But for the most part, it's pretty good. And so the actual values, so we ran this before we regionalized, and I gave my predictions for what things should be. And then we saw, here's the predicted assessment, here's what the state actually told us, and here is the difference. So the sum of the predictions is 100%. We're pretty close. The amount we're missing by is about 0.24%, 0.04%, 0.28%. So the total in Chapter 70 funds is about $3.5 million. 1% of the total is about $35,000. 0.3% of the total, which is larger than any of the numbers here, is about $10,000. So the school budgets, Lanesville Elementary is about $2.7 million, Williamstown Elementary $6.6 million, and then middle high school about $11 million. If we're off by around $10,000, that is a small amount relative to the budgets of the schools. And again, whenever you look at numbers, you always want to put them in perspective. For an individual, if I were to give you $10,000, that's probably a sizable amount. If I were to change the US budget by $10,000, it wouldn't be noticed. And so I'm not saying $10,000 is unimportant, but relative to the size of the budgets, the errors that are being made by the method of least squares, by linear regression, this is well within the range of what we can live with. So let's look at some other examples. So there are many nonlinear relationships which we've remarked are linear after applying logarithms. So if we have a power law, y equals b times x to the a, then when we apply logarithms, we get the log of y is a log x plus little b, where little b is the log of big B. And so let's look at Kepler's third law. So Kepler had 3 laws of planetary motion. The first is planets travel around the sun in ellipses. The second is if you draw a line from the planet to the sun, it sweeps out equal areas in equal times. And then the third is the one that this is not like the others. If t is the orbital period, traveling in an elliptical orbit about the sun, then t squared is equal to some constant times L cubed, where L is the length of the semi-major axis. This is a monumental achievement that Kepler was able to find this nonlinear relationship by poring over data assembled by many masters. So assuming we didn't know this, could we somehow figure this out through statistics? Well, we might as well take the exponent t squared is b tilde L cubed and just take the square root of both sides. And if you were really looking at the slides, you would have noticed that there was a b tilde, because I don't really consider b tilde the fundamental constant. I consider b the fundamental constant. So t, according to Kepler, should be proportional to the 1.5 power of the length of the semi-major axis of the ellipse. So that's the longer axis of the ellipse, the long direction. So how could we discover this? Well, here's a bunch of data. So here are the semi-major axes of the various planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. So I will sadly accede to the new convention that Pluto is not to be considered a planet, but for the purposes of this analysis, you could absolutely use that data. And then we have the data in orbital periods and years. So 0.24, 0.61, 1.00, 1.88, and so on and so on. Now, we believe t equals b times L to the a. We want to try to figure out what a and b are. If you look at this data, you should actually be able to figure out approximately what b is. And it's because we're using good units. So there are a lot of interesting units. If you want some good ones to look up are the Bruno, the millihelen, the slug, the smoot. I've given you a link where you can go and find out more about some fun units of measurement. I'm going to highlight one of the planets. I'm going to highlight Earth. So we've chosen the length of Earth, the length of its semi-major axis to be 1.000. And we're measuring things in astronomical units, where basically the Earth is 1 unit from the sun. And its period, we're measuring things basically in years. But we've got to be a little bit careful because a year is not constant. We have the leap year, the leap day that occurs, and there's all those different rules on it. But what's nice about this is we've chosen units where capital B should be 1. And so your homework is to try to find what the best fit values are. So if big B is 1, then little b, which is its logarithm, should be very close to 0. And so when you do your analysis, you should see a plot like this. And your homework problem is to figure out what is the best fit value of a and b. Is a close to 1.5? Is b close to 0? To just end with some interesting, fun tidbits about units. So this is the Harvard Bridge. It's about 620.1 meters. Many years ago, a fraternity at MIT decided they wanted to measure how long the bridge was, but not in the standard units, but in smoots. So smoot, shown here lying down, was a pledge to one of the fraternities at MIT. And what they did is they picked him up and marked where his head was, then picked him up, marked where the next head was, and marched down the bridge and measured how long the bridge was. And they got it was 364.1 smoots plus or minus an ear. I love the error and the uncertainty there. Well, the Cambridge police were not thrilled with this. The smoot marks were erased. The fraternity was not thrilled with this. They did this again. It went back and forth, and eventually the smoot marks were just left. And they've become an endearing mark of the bridge and the region. And in fact, when there are car accidents on the bridge, they report where the accident was as a function of how many smoots from the end of the bridge. Now, why am I talking about all this? Well, the story has a very interesting ending. You want to seize opportunities, you never know where they will lead. So Oliver Smoot, the student who was used as the unit of measurement, eventually became the chairman of the American National Standards Institute and the president of the International Organization for Standardization. You want to have compelling stories. You want to have ways to get yourself noticed. And the last problem I just want to end with is the birthday problem, which many of you may have heard of as the birthday paradox. So normally you would do this on Earth where you have 365 days, but I want to allow myself to have a variable number of days in the year. So the question is, how many people do we need in a room to have a 50% chance that at least 2 people will share a birthday? And we'll assume that all the birthdays are independent and uniformly distributed, so every day is equally likely. So we don't have identical twins. Another interesting twist is we don't have hockey players. The distribution of hockey birthdays and a lot of sports is actually not uniform. And there's some interesting reasons for that. So you always have to be careful about your data set. The reason for sports is when you're young, you actually want to be the oldest kid who just misses a cut to play up, because then you'll be playing with kids who are younger than you. Typically, when kids are small, being older means you're bigger. That gives you an advantage, so you look better, so the coaches like you more, so you get more playing time, so you get more access to special things. And amazingly, that trend propagates all the way up into the professional leagues. If you do an analysis, there's actually a nice formula for approximately how many people you need before 2 people share a birthday. It's roughly the square root of d times the square root of the log of 4. So what we can do is we can do an experiment. And so what I did is, I said, well, let's guess that it's some constant times d to the a. We'll take logarithms so we have a nice relationship, and let's gather some data. So I ran 10,000 simulations, and I chose the number of days of the year to some random numbers from 10,000 to 100,000. And the best fit lines I got for the first one was 0.506, and b was negative 0.011, and for the second, a was 0.48, and b was 0.23. So again, in both cases, we're seeing that we're doing a really good job of getting the exponent, of getting the value a. And that's the most important of the quantities. We're not getting as good of a job on the constant here. And we've now seen this in several situations when we do the method of least squares. We saw it first with the spring data. We're now seeing it here with the birthday problem. We do a much better job with the exponent than we do with the constant term. Well, fortunately, it's the slope that's more important, because when you're very, very large, that constant is not going to affect you that much. And what really matters is if I increase my x by a little bit, how much do I expect y to change by? So this ends our 3rd lecture on regression. So what we saw in this lecture was we saw applications. So we saw a variety of problems, some theoretical like the birthday problem, which actually has applications in cryptography and attacks, to some real applied ones, such as allocating money in the school district, where linear regression is able to give us really good formulas to approximate what's going on. And the value of the regression is to use these predictions in new regimes, in new ranges. So that if we now have a new value, if we have a new year, if we have a new time period, we can predict what's going on. You can use this in a lot of things. You can use this in baseball data, trying to figure out what is the value of a player, or in trying to figure out in housing, how much is a house worth given its location, given the number of bedrooms, number of bathrooms, size of property, oldness, all these different things. So we will then continue in the next lecture with some more applications.